This is section 15.2, limits and continuity. The goal here is to figure out what limits mean and what continuous functions mean now that we have this slightly more complicated idea of a function. Remember, we're not dealing with one variable functions like we did in Calculus 1 and Calculus 2 anymore. Now our functions are often functions of two variables, like f of x, y equals 25 minus x squared minus z squared, minus y squared. We learned how to draw contour lines and contour maps and level curves for these kinds of functions earlier. Now we want to figure out, can we say when these kinds of functions have a limit or when these kinds of functions are continuous? Just to get our data types right here, we're now looking at where the input is a point in the plane. That would be like an x and a y. That's this kind. Where the input is a point in the plane and the output is a number, which we're usually thinking of as a height. These techniques will also work when the input is a point in space and the output is a number. We can't think of those as being heights, so we mostly won't talk about those this section. But basically, if your function has inputs of multiple variables, how do you say that those functions have a limit or that those functions are continuous? Okay, so let's jump into it. The main way that we'll start is we want to remember how limits worked in Calculus 1. So the main thing you had to worry about in Calculus 1 with functions was you'd have a function and an x value, c. And you'd be trying to figure out if the limit as x approaches c of the function is actually this number L. So c is an x value, and L would be a y value, an output value. The main thing we had to worry about was, well, sure, maybe the function heads for L from the left. That was written this way, as x approaches c from the left. But what if x approaches a different number when we come in from the right? Like maybe the function looks like this. Coming in from the right looked like this. X approaches c from the right. So this was the question. If you come in from the left and come in from the right, does the function always head to L? If it does, if it heads to the same value from both directions, then we said, great, the limit exists and the limit is L. It got a little bit, so this one, the way I have it here, this one does not have a limit of L. We can make an open circle here even. This function has the limit as x approaches c of f of x is L. Because as long as when you come in from either side, the function heads for L. Now, hopefully your Calc 1 class went into a little more detail about this definition, which is that it's kind of hard to actually use this definition. You can kind of see whether the definition is working out on a picture, but to get into a little more of the details of how this works, what we would do is we would say, okay, you challenge your enemy to give you an epsilon. Epsilon is it's like a challenge, and it's a tiny real number. Your enemy tells you, look, I bet you cannot keep the y value contained in this range. And epsilon is how far away your enemy challenges you to keep the y value. So epsilon, your enemy says, I bet you can't keep the function epsilon away from L. It's like totally out of control. And the way you respond to that is you have to be able to make a delta, which is another small number, such that I don't like the order of this, but such that as long as you keep your x value close to c, so that's written like this, as long as your distance from x to c is below delta and above 0, as long as that happens, then we can keep our y values in this range, just a little bit away from L. And that would look like this, that the distance between the function value and L is less than epsilon. If you can make this happen, that like if no matter what challenge your enemy gives you, here's this challenge, is like try to keep the function in this range. And you say, no problem, here's a little bit of the function that's in that range. So I'll let delta be this distance. Your enemy could give you an even smaller epsilon, and then you would have to hand back an even smaller delta. But this was the official I don't know. There's different levels of definition, and this one is a deeper and more robust definition of the limit. On a picture, it ends up being basically the same. All that this ends up doing is it makes sure that no matter what direction we come at C from, we are still approaching L. But yeah, hopefully your Calc 1 class had some of this in it. Anyway, when we get more variables as our inputs, now things are a little bit dicey, because before, when we had just, we were trying to approach x equals c, you had to check, well, does the limit from the left come in at the same place as the limit from the right? Like, there's only two ways to get to x equals c. But now we're going to pick a point in the plane, x0, y0. I can't call it C, and I don't want to call it CD because D is kind of taken. So yeah, we'll call it a point in the plane, x0, y0. Ooh, not there. So as our points are approaching x0, y0, we want to know if the function value is approaching L. But the problem is I can't list like, oh, well, you either come from the left or the right, and you check the left and the right. No, it's not that easy anymore. Like, you can come from the left toward x0, y0, and you can come from the right, but you can also kind of like come from the top and the bottom, and you can come from like a weird like curvy direction that comes in at x0, y0 from a weird way. So for the limit to work in this situation, it needs to work from every direction. And even worse, I want to be able to say that it works even if you come in on some weird squirrely path. So we'll say the limit exists as long as the function approaches the same y value no matter how you come at the input point. Okay, how do we formalize this? Well, same deal. We're going to have an enemy give us an epsilon. And that's the enemy's challenge, which is to say, like, I bet you can't stay this close to L. And then our job is to come up with a delta, such that as long as you stay, again, this order, such that as long as you stay, and how do I write this? I want to write the distance. I don't really have an easy way to write that. I guess I'll write it as for all xy within delta of x0, y0. So our enemy says, I bet you can't stay this close to L. We say, well, we're fine as long as you stay this close to the base point, then we will be that close to L. Now, in the Calc 1 definition, being within delta of the target point meant you had an interval that was, well, you go delta to the left and delta to the right. But now we need to draw this picture. We need to be within delta in any direction. So that picture will now look like a little disk in the xy plane that has a radius of delta. Now there's one more thing missing from this picture. We've got the target y value, the target x value, we've got the challenge, which is the epsilon, and we've got the response, which is the delta. But like, what does the function actually look like? Well, the function in this case, as we tried to figure out in the previous section, is a surface. So I don't know, you want to think about like a wavy, like a fluttering, my example surface that I think about is like a fluttering blanket or like a fluttering bed sheet. And there's some point up here that we're trying to figure out what's going on as x and y get close to their x and y value. What happens to the various z values? So this point is like x, y, z. We're trying to figure out if you stay close to x0, y0, does the y value stay close to f of x0, y0? Cool. Okay, so how are you actually going to deal with this? Oh, we don't get to do examples yet? I want to do examples. I guess this is like good motivation to do the examples. Ugh. Okay, well, instead of having to look at a picture and say, well, when x approaches from the left and x approaches from the right, do we get the same answer? Instead, now, with a function of two variables, you have to say, when x and y approach our base point from any path, do we still get the same answer? So it'll be trickier. The main thing we'll want to do with this is figure out if a function is continuous. In Calc 1, a function was continuous if the limit equaled the function value. So as in Calculus 1, where a function was continuous at x equals c if f of c was the same thing as the limit of the function as x approaches c. We say that our surface, the function that defines the surface, is continuous at this base point if the function value matches the limit. Now, instead of saying x approaches c, like in a single variable function, the input was just the x. Now the input is an x and a y. So we have to let x, y approach x0, y0. So it looks more complicated, but it's the same idea. The only thing about this that is actually more complicated is that there are infinitely many directions to check instead of left and right. Okay, so how do we actually deal with this? Basically, just like in single variable calculus, we normally, like our normal way out is to say, okay, there's some functions that just behave nicely and we know not to worry about those. So like for nice functions, as long as the point xy is in the domain of the function, like as long as it's possible to plug the number in, then we know that the function will be continuous there. So the nicest kinds of functions are, let's say, like polynomials are the best. Trigonometric functions are nice and continuous as long as we're on their domain, which is what we're figuring out here. So if you've got like a tangent in your function, it's continuous everywhere except where tangent is not defined. Similarly, any like logarithmic or exponential function. Logarithmic functions will have domain issues, and you just check the domain issues, and then other than that, you're just like, fine, it's continuous everywhere. And then any, I guess, like I want x to any power to be here, and I've got x to positive integer powers. So I want to make sure I mention like radical functions. Like if you have a square root, that's fine as long as you're in the domain of the square root function. And any rational functions are okay too as long as you're in their domain. So this rule, unfortunately, like is mostly what you'll end up actually doing. You'll look at a function and you'll be like, you know, the function's fine, like there's nothing crazy going on, so it's continuous, except maybe at these places. So let's see how this works in practice. So we say, let's find the limit as xy approaches 1, 4 of this function. What you do is you say it's a rational function. So it's continuous on its domain. And because of that, the limit is the same thing as just plugging the numbers in. So the limit of 10x minus y over xy squared is plug in 1 for x and 4 for y. So I get 6/16, which is 3/8. This should be what you remember of calculating limits in Calc 1 or whenever you calculated limits last, is that normally your primary plan for dealing with a limit is to just plug in the target number. If the target number is not in the domain, then things will be a little more complicated. I want to get some pictures of these. Let's see if I can get a picture of this in GeoGebra. So we'll use Desmos when we're graphing single variable functions. Desmos is the best online graphing calculator for that situation. Here, I'm going to use GeoGebra. You go to geogebra.org/3D. Let me get I don't have any Maple stuff ready. So you do, I'm just going to write the link here, which is a little awkward, but since this isn't a word, geogebra.org/3D is good for this. The function we were looking at was f of xy is, so I'm going to write z equals 10x minus y over xy squared. Now, what's going on here is we are thinking of this function of two variables, the inputs are x and y, as having you input an x and a y, which is a point in the plane, and then the output tells you how high to go. So above each point in the plane, you can put a point that's its function value. If you get negative function values, then you put the point down below, and then you connect it all up and you get surfaces. So that's what we were doing with level curves before. GeoGebra lets you plug in the function, and then, whoa, I didn't know you could let go and let it rotate. Okay, that's awesome. And then it shows us that like this surface is all broken up in all different places, but it's not broken up at the point 1, 4. The point 1, 4, let's see if I can. It did draw it. It's this blue point right here, 1, 4. At x equals 1, y equals 4, the surface is not broken. Like this is, not only it's in the domain of this function, but also the function is a rational function, so it's continuous on its domain. So we can see that above the point 1, 4, the z value, the height, is 3/8. 0.38? No, that's not. Oh, it's probably close enough. So now this blue point at 1, 4, 3/8, you can see it on the surface. And no matter what direction we come at this point from, as long as we approach this point on the surface, we end up at the same y value. So the limit exists and we get 3/8. And this is the most common situation, is that like you look at the function has no problems at the point that you're interested in. The point is in its domain, and so you just plug in the point and you get the answer. Now this one, not so lucky. The point 0, 0 here, x equals 0, y equals 0, makes the denominator 0. So I cannot possibly plug in 0, 0 here. If I do, I'll get 0 minus 0 over 0 minus 0, which is 0 over 0, and that's not a number. Hopefully you don't get 0 over 0 and say that the limit does not exist, because things like 0 over 0 are actually indeterminate forms. It means 0 over 0 could be anything. I have no idea what it is. Sometimes it's 0, sometimes it's infinity, sometimes it's 8. So how do you deal with this? Well, first of all, please don't use L'Hopital's rule, because L'Hopital's rule is a fact about single variable functions. If you go in here and you start like taking derivatives of stuff, that's not going to work. Like, what do you mean, the x derivative or the y derivative? Like, where do we even start here? So don't use L'Hopital's rule. It's not a thing. Instead, you need to use some algebra like we did in Calc 1. So here's how we do that. We say, well, sure, you're dividing by x minus y. So I've got x squared minus y squared over x minus y. But the numerator has a factor of x minus y. This is going to annoy you that I'm writing this again. I don't know. I want to write equal signs between things that are equal, and in order to do that, I have to write the limit again. So I can factor the numerator, and then here is the culprit. This is where the 0 over 0 is coming from. Normally you can't cancel 0 over 0 and get 1, but inside a limit, you're fine to do that because the limit doesn't care about any one point. So this 1.00 is not, this is not a point that we care about inside the limit, so we're able to actually divide these. So now we end up with the limit as xy approaches 0, 0 of x plus y. Now we're in the domain of a polynomial function, so the function is continuous. So the whole thing equals, well, just plug the number in. You plug in 0 plus 0 and you get 0. In this case, 0 over 0 was 0. Please believe me that 0 over 0 is not always 0. It doesn't always work that way. Let's get a picture of this. Apparently, I don't know if you remember this from Calc 1, but when you had factors that canceled like this, and then after the cancellation everything worked out, that meant there was a hole in the graph. So here, there's apparently a hole in this graph also, but it's going to be a hole poked in a surface. Let me pull up this. So we're going to do z is a undefined. That's not what I want. Z is x squared minus y squared over x minus y. So this function looks like a plane to me. It's just a flat plane. But the problem is that it's a flat plane where the only thing that ever goes wrong is if x happens to equal y. Ooh, can you see it fracturing there? If x happens to equal y, you can see it like trying real hard to, it's like, oh, maybe I should, oh no, maybe it's fine. Oh no, I'm not sure. If x equals y, you get 0 over 0 and the plane isn't there. So, I mean, a computer, the computer is trying its best, and the best info we can get from the computer about what's happening along y equals x is that there's trouble. But from the algebra, it's easy to see that y equals x makes the function undefined. So this graph is actually a plane that's missing an entire slice. It's actually, there's like a infinitesimally thin cut through it. It's just been cut in half. That's okay though, the limit still exists. No matter what direction we approach 0, 0 from, we still get, we still approach 0. So we're good. Okay, on to the next thing. The next one looks pretty doomed to me. Okay, we're trying to evaluate as xy approaches 0, 0, 10 over x minus y. Okay, again, we're in trouble here, where if you plug the number in, if you plug in x and y, you get 10 over 0 minus 0, which is 10 over 0. I don't know if you remember this, if this was in your Calc 2 or your Calc 1, but 10 over 0 is not indeterminate. 10 over 0 is a clue that everything is so ruined that there's no way that this can work out. So if you don't remember how the indeterminate forms work, you should, I guess, look up a list of indeterminate forms and you can see what kinds of things they are. But 10 over 0 is not one of them. This limit does not exist. Let's get a picture of this one. 10 over x minus y. Over x minus y, well, it's, oh, I didn't switch the view. Okay, 10 over x minus y looks like this. So above each point, x, y, you plug in x and y into the formula, and you get the height. And, well, along the line y equals x, everything is ruined, but it's like ruined in a more horrible way than for the other surface. This surface is not headed to any particular height, any particular z value as x and y approach 0. Instead, from different directions, from some directions you're headed off to infinity, and from other directions you're headed down to minus infinity. This limit absolutely does not exist. Okay, on to the last page, I think. Okay, here's some examples. So I guess the hardest part of these is that you're not really sure how to decide. Like, you don't really know in advance if the limit exists, but yeah, let's see. So let's try to plug in 0, 0. If you plug in 0, 0, you get 0 over 0. That's indeterminate. So that means there's a chance that the limit exists, and there's a chance the limit does not exist. Now, if the limit exists, we would need some kind of algebra miracle to save us here. Like, something would have to factor and cancel. We don't really have the analysis tools to prove that a limit exists unless something good happens in the algebra. We do have the analysis tools to prove that a limit does not exist. So I look for some factoring. Nope. So, like, probably it doesn't exist? Probably. Probably it doesn't exist. How do we show that it does not exist? So you've seen an example where it was an indeterminate form and the limit did exist. You've seen an example where the limit did not exist because everything was a disaster. Here's one where the limit is indeterminate, but it still does not exist. How we show that is we pick two paths to approach 0, 0 from, and try to see if approaching 0, 0 from those two different paths gives us two different answers. So choose two paths. If the limit comes out different on the two paths, then the limit does not exist. This is basically exactly the same plan that you would have used in a Calc 1 class. You would say, I'll come at it from the left and I'll come at it from the right. And if I get different numbers, then the limit does not exist. But here you have lots more paths to choose from. So if the limits are different, then the limit does not exist. Usually the best paths to use are simple paths. Now, what do the paths look like? Well, a path would be any function or any curve in the xy plane. So the easiest paths to use The easiest paths to use are things like x equals 0, which means just come at this point from the y-axis. Just come at this point along the y-axis and see what happens. Y equals 0 is also an easy path. Sometimes in situations like this, where x equals 0 and y equals 0 are completely out of the question, you want other paths. So you say like, okay, well, I need any other easy curve in the xy plane. And the easiest one is like y equals x. Is a line that comes in diagonally, and another one would be like y equals minus x. If you can't use two of these, then you just keep naming functions that like easy curves that you know. So after this, the next tier would probably be like y equals x squared. But you can literally use any path as long as it goes through the point that you're headed for. These are all set up so that they head through the point 0, 0. So let's try two of these. So I can't do x equals 0, because if I try to approach along the path x equals 0, I will do that by plugging 0 in for all the x's to start, and then the whole thing is ruined, so that's not good. So I can't use either of the zeros. I'll use y equals x to start. So if y equals x, then my function y equals x. So my function is actually x minus x, because y equals x, over x squared. So the function is 0 over x cubed. So what I did here is I substituted y equals x into the function, and I get a simpler version of the function, which is that the function is always 0. So this function is headed to 0 along this path. Let's try y equals minus x, because it's the next easiest path. When I plug in minus x for y, I get x minus minus x over x times minus x squared. So I get 2x over x cubed, and that's 2 over x squared. Now, 2 over x squared might still head for 0. So what you do is you say, okay, since y equals minus x, that's fine. What are we actually looking at? Well, we're sending both x and y to 0. So here, since I've got everything in terms of x, that corresponds to letting x go to 0. Well, what is this limit? As x approaches 0, 2 over x squared? No, that doesn't head for a number. This does not exist. So whatever this surface is, if I come at 0, 0 from one angle, the surface heads to 0. And if I come at 0, 0 from a different angle, the surface heads to infinity. So if you go different places from different directions, then the limit does not exist. So since these were not the same, we say that the limit does not exist. Cool. Let's look at a picture of this. I want to see a surface that when I come at it, when I head to the origin in different directions, I get different answers. So this was x minus y over xy squared. Okay, where is y equals x? So here's y equals x. Y equals x is this plane. If we follow along the surface and we follow y equals x, the surface is stuck at 0 along y equals x. As long as y equals 0, everywhere along this surface where the height is 0, the height is 0, the height is 0, the height is 0, and the height keeps heading for 0. So along this path, along the y equals x path, the limit was 0, and that's what we got before. Now when we instead look at y equals minus x, which is coming at it in this other direction, now you can you see the slice? That the intersection, now instead of being at 0, 0, 0, 0, 0, now we're like zooming off to infinity. And that shows that if we approach 0, 0 along y equals x, the function is headed for 0. And if we approach 0, 0 along y equals minus x, the function is headed to infinity. Since we got different answers, there was no chance for the limit to exist. The surface is kind of crazy. It's definitely got problems at 0, 0. Ooh, that looks really cool. Huh, neat. Okay. On to the last example. Okay, this looks like a total mess. Oh, there's two. Oh, there's a bunch more. Okay, let's see. Oh, the ones where is it continuous are a lot easier. So this one we want to evaluate the limit as xy approaches 0, 0 of all this stuff. Okay, well, my plan is to plug in 0, 0 to start. I get 0 minus 0 over 0 plus 0, and it's all squared, and that's 0 over 0, which is indeterminate. So I'm hoping for some algebra thing to save me, but x squared plus y squared does not factor, so there's no way for any algebra to help us. So we suspect that it does not exist, and we pick two paths. So let's approach 0, 0 along one path, and then along another path. And you can literally pick any path. So for me, I'm always going to try to pick the easiest paths I can, and x equals 0 is the easiest path I know. So along x equals 0, I get that my function is now, well, x is 0, so I get minus y squared over y squared, which is minus 1 squared, which is 1 everywhere. So the function is 1 everywhere. So along x equals 0, f of xy approaches 1. Now let's try another one. If we approach 0, 0 along y equals 0, that's the next easiest one. Plug in 0 for y. We get x squared over x squared squared, and that also approaches 1. So we got 1 on both paths. So the question is, does that mean the answer is 1? No. So we only get to say that the limit equals 1 and that it's over if we've literally checked every path. This doesn't check every path. And we also don't even have a way to check every path. So in this class, because it's a 200 level class and we don't have the firepower to prove that these limits do exist, whenever anything goes wrong, usually you can tell that the limit does not exist, and you just have to be a little bit more creative and try a different path. So let's approach 0, 0 along some other path. I don't know, y equals x seems fine. We're basically on the hunt for 2 different paths that head to 2 different places. So now I'll plug in y equals x. Now it's x squared minus x squared over x squared plus x squared, all squared, and that's all 0 all the time. These don't match. If the limit existed, then we would get the same limit from every path, so this limit does not exist. Cool. Okay, let's do these last ones where we ask where a function is continuous. To find out where a function is continuous, we know that since these are rational functions, that they are continuous on their domain. So all of our nice familiar functions are continuous on their domain. Its domain is all the places where the denominator is not 0. Okay, well, when does x squared not equal 0? That's all the places where x is not 0. So this is a fine answer. A more technical way to write it is you say, I want the set of all the points such that x is not 0. So if you basically have to decide to either learn the technical notation or write words. They're both fine for me. You should, if you have another professor, you should ask the professor what they prefer or if it matters to them. But you can write some words to describe the domain, to describe where it's continuous, or you can write the technical way to do it, which is less writing, but you have to learn how to say this. So the set braces guarantee that we're talking about a bunch of different points, and this colon means such that. So this is all the points x, y, such that x is not 0. This one, same deal. It's a rational function, so it's continuous on its domain. Its domain is all the places where the denominator is not 0. So we need y to not equal x squared. So that means the domain is everywhere except the parabola y equals x squared. I want to see this one in a picture. Apparently this surface, whatever this surface is, it's totally smooth and reasonable, and it's all connected up nicely, except right above the parabola y equals x squared. So we'll look down from above y equals x squared, and we'll see that the surface is all busted up along that parabola. So I'm going to head back to GeoGebra and try to get that to show up. Y minus x squared. What was the numerator? Just 2. What? y minus x squared. And in the numerator, I want 2. Neat. So this surface is totally reasonable and smooth, except it's in 2 pieces. And along y equals x squared in the xy plane is where it's broken. So this surface is 2 surfaces, and it's discontinuous at all the points where y equals x squared. Okay, so that was section 15.2. The point of all of this was that limits are complicated when you're dealing with functions of multiple variables, but that's okay. Usually you can get out of dealing with complicated limits by just plugging the points in. And we've got a list of all the nice functions where as long as you can plug the points in, as long as you are in the domain of the function, you can find limits by plugging the numbers in. If you're not in the domain of the function, because the denominator is 0 or something, you get out of it by doing some algebra that saves you. That was this. Or you say, well, this is unsalvageable. It's outside the domain in a really bad way. Or in the harder cases, you go look for some different paths to approach your point from. And if you can find 2 paths that lead to different limits, then the limit does not exist. Yeah, that should do it.